In this final video on graphs, we are going to cover an algorithm called topological sort. So a topological sort is an ordering of vertices such that if there is an edge from Vi to Vj, Vi will always precede Vj or Vj will come after Vi. This has nothing to do with vertex labels. So let's say if we have something like 1 connected to 2, connected to 3, and so on, or 1 is connected to 4, that doesn't mean that we are trying to sort this in numerical number, because the labeling doesn't make sense here. What makes more sense is whether an object comes after or before any particular other node, or if we try to model different processes, or if we try to model different problems, we are basically trying to find dependencies of which node is dependent on another. So this algorithm works only on directed graphs. And a couple of examples, like you can see on the left, is one example where you are modeling the execution process of baking an item or creating like some spaghetti or something like that in the form of a graph. Another example could be if you're modeling how you wear clothes in your daily life, you can model that in the form of graph. And there are some clothing items that you'll always wear before another one, which is like you will never wear a tie after before like wearing a shirt, for example. In this case, like you will never start the oven already after baking bread, and so on. So what we want is this serve bread can never occur before both of these tasks are executed or not, and that should reflect in a natural ordering. Another example is this course chart. So here we have modeled the entire university curriculum. This is not UF's curriculum, but some other curriculum in the form of a prereq chart, which is what is a prerequisite to take another course. If you try to model this, and if some student wants to find out which courses he or she should take in a certain manner, or they should take in a certain manner, they can just take the topological sorting of this graph to decide which courses they should take. Now, another thing to note is that topological sort is non-unique, which is there can be multiple ways to represent the sorting of this algorithm, although there are different constraints. Like you can have uh, you can have served bread. You cannot have like serving bread before baking bread, but you can have some tasks that can be independently performed in parallel, so they can be executed at any moment, which is like in case of let's say programming one. If you are taking a programming one course, you can take parallelly a chemistry course because it has nothing to do with it, and so on. So this is like non-unique. So let's discuss a simple algorithm to find the topological sorting. So how this works is we have a data structure like Q, and this keeps a track of the nodes that we are processing. Another one could be a vector, or it could just be the print operation, which is we are just printing what is the sort order. So how this works is we are first going to place all the vertices that have in degree equal to 0, or they have no edges that are pointing to them, which is in this case 0 and 5 have no vertices that point to them. So just to recap the terminology that we use here, a node has in degree or no incoming edges, then its in degree is 0. And if the node has no outgoing edges, then its out degree is 0. Okay, so 6 and 7 have out degree 0, 3 has also out degree 0, while 0 and 5, these are the nodes that have in degrees 0 because they have no nodes, no other edges that point to these vertices. So what we are going to find first is what are the vertices that have in degree equal to 0, or those who have no incoming edges. We add that to the queue in any arbitrary order. So we don't care whether we add 0 or 5 or 0, but let's say for the purpose, I'm just adding 0 first and 5 another one, but it could be in any order. Next, what you're going to do is like V0 is keeping track of the queue and sort order is keeping track of the sort order. It could be a vector or anything like that. Next, you're going to pop an element or dequeue an element from this queue, which is in this case 0. You're going to print that or add to the sort order. Next, you're going to decrease the in degrees of this node 0 by 1. You're going to remove this node and then decrease the in degree of all the adjacent nodes. So in this case, 1 and 4's in degree will be reduced by 1. Essentially, we are deleting this node along with its edges. Next, we are again going to pass and see which are the nodes which have in degree 0. So now 1 will also have an in degree 0, but 4 still has one more in degree, which is 5. So we are going to add 1 to our queue, which is initially our queue was 0 and 5. 0 got, like, we removed 0 from the queue, and now we'll have 5 and 1 into our queue. Next, we are again going to remove the front element from the queue. We are going to delete this and add any new vertices whose in degree is 0. So in this case, 1 and 4 will be in our new queue and 0 and 5 are already printed. Next, we again pop the element from the queue, which is 1. We delete all the edges that come out of it. Now you can see 3 and 2 are still connected, but 7 has like in degree of 0. So in this case, we are going to add 7 to this. We are going to print 1. So we have 4 and 7 and 0, 5, 1 in our print queue. Next, we are going to pop again the front element from the queue, which is 4. Now, after popping 4, we'll have just 2 and 3 will also be will have no incoming edges. So you are going to add 2 and 3 to this order or to this queue in any order. So again, like there could be multiple answers for the topological sort, and you will have 0, 5, 1, 4. That's one of the answers. Next, you have added 2, 3 to the queue, like you'll remove 7, which is you'll remove 7, add that to the queue. It doesn't affect any in degrees, so you're good. Next, you're going to print 2. Now 2 affects 6 in degree because we are decrementing that by 1, and we'll add 6 to this queue. So we have 3, 6 in the queue, and the rest is already sorted. Next, we are again going to pop the front element, add it to the sort order. Then finally, we are going to print 6, and our V0 is empty or our queue is empty. So we are going to process this algorithm till our queue is empty. This is the pseudocode for the topological sort algorithm. Again, we are maintaining a queue. We are making sure that our queue is not empty, and initially we are adding to that queue all the vertices that have in degree equal to 0. So this is one way to implement it, which is when you are implementing the graph, you are keeping track of in degrees. Another way to perform topological sort, like there are hundreds of algorithms to perform topological sort. You can do them in several ways. This is just one algorithm. Another way is like using DFS. So in the DFS, when you add items to the stack, if you manipulate the DFS such that you kind of like do a post order DFS, which we do not discuss in the class, but if you read more about it, there's something called post order DFS, which is you process the node not at the time when you add things, but when you remove things from the stack. If you reverse the post order DFS, that's also will give you a topological sort. So there are multiple ways of doing it. This way, the disadvantage of doing it this way is that our graph could be destructive, which is when we are changing the in degrees later on, if we do not make a copy of that object, if we create a copy, that is going to be more memory, like it will consume more memory. But if we do not create a copy of the object, it's going to destructively change how our graph will look like. So that's not good. So like another common way is post order DFS, which we don't discuss in the class, but if you're curious, just search how to do topological sort using post order traversal, or the depth first traversal of the topological sort. So here we are going to dequeue the element as we saw, and then we are going to increment. Like here you can actually print the next number or whatever, that's absolutely fine, whatever you are trying to do. Next, you are going to find what are its adjacent elements. Like in this case, what we are trying to do is, like let's say if we are trying to change or process the next node, we are going to find what are its adjacent elements, and next we are going to decrement their in degree, because that's what we are trying to remove. And again, if the in degree, the decremented in degree is equal to 0, we add them to the queue. So this method can also be used to detect cycles. Like if the counter is not equal to the number of vertices, which is after deleting, if you still do not have that equal to the number of vertices, this can also be used as a method to detect cycles. We are not going to discuss it because we have already discussed a couple of methods. That's pretty much it. If you have any questions on the topological sort, feel free to ask me. Try to analyze what would be the time complexity of this. Typically, it would be like, since there are v vertices which are independent, and then in the queue there are e edges, so it should be like v plus e, which is pretty much similar to the breadth first traversal or the depth first traversal for graph. Thanks.